Hello, everyone, and good morning. Today, as Katie mentioned, I will be talking about meta transfer learning for MOOCs and early success prediction in them. I'm here on behalf of a great team of collaborators. I come from EPFL. I'm a second year PhD student there. And alongside professors Mirko Marras and Tanja Käser, we're really excited to bring this work to you today. So as we well know in this community, deep learning has been increasingly researched in digital learning environments. In the context of MOOCs for dropout prediction, in student knowledge tracing, in auto grading, plagiarism detection, in the last 7 years or so, there have been a plethora of literature using neural networks for these educational contexts. So the question remains, why is there still an adoption gap? When we look at the poster sessions from yesterday and a lot of the work that's at this conference and at many others, we usually see simpler machine learning techniques and different other kinds of models that are being integrated into these practical learning environments. And there's still an adoption gap between neural networks and digital learning in general. And so when we think about the situation which causes a model to be trained for this context, we first have students in a digital learning environment, like a MOOC. And from that, we want to train a model on a task, let's say like student performance prediction. Can we say from 40% of a course, whether a student is going to pass or fail the course and predict that early enough? Other tasks include dropout, affect detection, and various others. But to train this kind of model, we kind of need a supervised training problem. So for the students in the course, we need to already know whether they passed or failed a course, as well as all of their interaction data. But when it comes to ongoing or first-time courses, we now have a problem trying to make those predictions, as well as the small data set sizes in traditional classrooms. So how do we train these models for students that we are seeing for the first time? And so in many settings, in general, it is kind of impossible to train an ideal model for early student success prediction. But of course, as many of you know, there has been a lot of work in this area. And what the general solution is a professor has a class. They usually have previous iterations of this class. So they offer it, let's say, for the third year. And then they have 2 years of data on their previous students in this class to train a model on and make predictions. Alternatively, there have been a few recent papers from MIT and various others that explore transfer across just a few courses in one context. So in this paper, they look at some of MIT's very famous programming courses, but just 2 of them in multiple iterations. There is still a gap if it's an ongoing or a first-time course, or if you can't find a similar course to train a model on. And that's what we hope to address with this research. So the objective of this paper is therefore to use meta transfer learning to develop these early success prediction models that can be applied across diverse domains. Essentially, we make the argument that not everyone has to train their own model for their case. They can use one big, large model trained on a very diverse data set of MOOCs to warm start their predictions, even if they don't have a lot of data about their students. So the data set we're looking at has 26 MOOCs collected in Switzerland. So it's hosted by EPFL, the university that I'm at, with millions of student interactions from a very diverse set of courses. And in terms of machine learning methodologies, I mentioned this term meta transfer learning. It's quite new in the machine learning community as well, so I'll break it down a little bit. Meta learning is the concept of generalized learning at scale. So if it's, you can think of meta learning as learning how to learn. You pass in meta information about the task you want to predict on to your model, and it performs better with that knowledge. So if you're training on a couple of different tasks, let's say success prediction on an English class versus a math class, you can pass in meta information to contextualize the predictions that it's making. And then we also look at transfer learning. Transfer learning is the concept of training a model in one context and then taking that model and applying it in a second context by fine-tuning the predictions a little bit for that new data scenario. And so combined, they are meta transfer learning. In this work, we framed 3 research questions. The first one is looking across a diverse set of courses, can student behavior transfer? Can we use this model to make predictions across this diverse range of courses? The second is a meta learning model trained on a combination of behavior data from the students and meta information. Does it perform better? Can we use meta transfer learning in this context? And 3, if we do have previous iterations of a course, can we use those to make the predictions of our model even better? And this is a common concept known as fine-tuning in natural language processing and computer vision. It's used quite a lot. So our pipeline looks a bit like this. It's an intimidating diagram. We will zoom into each of the steps, starting with data collection. So we have 26 different MOOCs. From those MOOCs, we have click streams, which I'm sure you guys are familiar with from Coursera and edX and various others. Our click streams mainly derive from video interactions as well as quiz interactions with problems. We also have metadata about the course, and we'll dive into that a little bit further. But one interesting point is that when we're looking at these MOOCs, there is a big problem with dropout. It is very easy to predict for some students that they are going to fail from a technical perspective the course because they simply don't do any of the assignments. And at that point, why does it make sense to train a complex machine learning or deep learning model on these students when really any teacher can look at their first 2 assignment grades and predict that they're going to fail? And so we remove all of these students from our model originally by training a very simple out-of-the-box logistic regression. And when our logistic regression model says with 99% confidence a student is going to fail from just the first 2 weeks of assignment grade input, we remove them from our original training data. And the benefit to this is that it actually makes our model train faster and better on the students that we really want to care about and are interested in creating accurate predictions about, as well as not wasting computational resources for students that we can predict very easily. Our dataset has, like I mentioned, 26 different MOOCs. They range on a variety of different topics. We select these 6 to highlight. And digital signal processing, Ville Africaine, because we're in Switzerland, some of the courses are in French. That's urban cities in Africa. Structures, which is an architecture course, and various others. Venture, which is about venture capital from a business background. And some of them have only 1 iteration. Some of them have previous iterations. Some summary statistics about the data. The languages they're offered in are English and French. The student levels that the course is tailored for are bachelor's and master's. And there's also this concept called propedeutic, which is the first year of a bachelor's course. Of course, because it's a MOOC, anyone can take it. So those levels, you can take them how you will. There are students, the student sizes for these courses range from 95 students after removing the easy fail students to 19,000. Between 5 and 15 weeks with pass ratios between 1% and 65%. And a variety of different quizzes integrated in these courses, and the amount of quizzes and how important they are being different as well. So clearly quite a diverse set of courses that we use to train this model. We then move to pre-processing. So as I mentioned, we want to do early prediction. So we want to be able to intervene with our predictions and actually change student learning outcomes if they're predicted to fail. And to do this, you have to predict early in the course. So we look at both the 40% and 60% cutoffs of student interaction and predict whether they pass or fail based on that. We kind of throw away the rest of the course. And now we move on to feature extraction. So we extract 45 behavioral features, and these are all derived from previous work. Specifically 4 different papers. The reason we choose these feature sets is that a recent paper from Marras et al. At EDM implemented hundreds of features from related literature and found that these feature sets were particularly good for MOOCs. A lot of them are about video performance data, whether students are actively checking on the course, whether they do a problem and get it right on the first attempt, things like this. We also have meta information, and so I will dive into this in more detail. So behavior features are features derived from the student clickstream. Of those, we have 45, and these are extracted for each week for all the students. And then we also have meta features, and these meta features are derived from the metadata about the course. We have 3 textual features. So one is the title of the course. We then have the short description and the long description. The short description is 1 to 3 sentences. Long description is 4 to 5 sentences. Think about it like a course catalog. And we want to figure out some way to pass that information into our model. The hypothesis here is that if you have a new course you want to make a prediction on, and we have our very diverse set of of courses that we currently have, how can we place it in the space of courses such that it can contextualize the predictions with the notion that similar courses about similar topics might have similar types of students and similar learning styles? And so we tried 3 different models that are state of the art for textual encoding: SentenceBERT, Fast Text from Facebook, and Google's Universal Sentence Encoder. And after experimenting with all of them, we found Fast Text works the best. We also pass in information about the duration of the course, so the number of weeks, as well as the level of the students, bachelor's, master's, and language that the course is offered in, French, English. So now moving on to the models that we use. We have models trained as baselines on just the behavioral information of the course. And then we also want to pass in the behavioral and meta information about the course to our downstream models. And we pass in the information, the meta information, in 2 different ways. We first start by passing it in at every time step. And then the second way we do it is passing it in once and telling our model to pay attention to it. So I will dive into these in more detail as well. But our evaluation metric that we use is balanced accuracy. The accuracy numbers for student prediction models in MOOCs are generally very, very high. The reason for this is that a lot of people fail. And so a model will perform very well if only 10% of the people pass, and it just predicts everyone fails because that's 90%. What we really cared about is making sure that we can predict that students who are going to pass, or that borderline, are predicted as passing versus failing. And so balanced accuracy lets us enable to put the same weight on failing students as passing students. Okay, diving deeper into our models, we first look at behavior only. So passing in our 45 behavioral features about a student to a bidirectional LSTM, which is a model that takes advantage of time series relationships between our data. We fit it in a sigmoid layer, and then we have our predictions, the likelihood that they will pass or fail the course. We refer to this as the BO model, or behavior only. We then start combining our meta information. So behavior plus time-wise meta essentially includes the meta information alongside the behavior features at every single time step. And we feed it into the same BioSTM. You're familiar with the rest of the model to get the predictions. Now, this last model is a little bit more complicated. We have our behavioral features, which we pass into our BioSTM. But instead of making the predictions directly with the sigmoid layer, we just take the results of the BioSTM. And then we also want to pass in our meta information separately. And so what we do is we take our meta information, but we want to contextualize which parts of the meta information are important. And so we add an attention layer. The benefit to this is twofold. 1, it tells our model what to pay attention to. 2, it lets us interpret what our model is paying attention to. And so we include this. And then we decide to project both of our features to the same space. The behavioral features are generally very different than the meta features. So we want to make sure that they're kind of comparable by projecting the embeddings using some other layers. And then we take the result of those and we put attention on them again. And the reason for this is then to see whether the model pays more attention to behavior features or meta features, or equally to both. And eventually throw some dense layers at it and finally get our predictions. Hopefully you follow, hopefully, otherwise you could ask me questions later. And so with those 3 models, we will dive into the results. The first question was, can student behavior transfer across iterations of the same course and across different courses? So we train on a couple of different settings, and we transfer on 6 courses that we pick for diversity in passing rate, in topic, in student population. And the first setting is, can we predict on the same course as training? For our digital signal processing course, can we make predictions? And this case will never happen because that would be us knowing the future about whether a student passed or failed. So this is kind of our best baseline we could possibly have. The second setting is we take one course and we transfer to a different course, and we average these results across all of the 6 courses we're looking at. Our third case is where we train on previous iterations of a course and predict on a current or ongoing iteration. And our last case is where we train on 20 courses and we predict on 6 and average across them. And what you will notice, looking at all of these results, is that all of the best models leverage either the previous iterations or the model trained on 20 courses. So what we see is courses with previous iterations where the student populations are quite similar to the current ongoing course. It makes sense to use the previous iterations. But otherwise, in pretty much every other class, and especially when they don't have previous iterations, training on different courses is better. So moving on to question number 2, can combining behavior or course metadata information, does it make our model more transferable or have better predictions? So we train on 20 courses and we transfer on 6 courses. This is almost the same setting that we saw before. So what we see first here is the baseline. This is if you had previous iterations, this is how good it performs for 6 different courses we look at. For the last 2, we don't see those columns because they don't have previous iterations. The next row is using the 20 courses, but not having any meta information. This column here is using the static meta, so adding it in with that complicated architecture, and we see that we do see significant performance increases. And the last case was time-wise meta, just passing in the meta information at every timestamp. And across the board, for 5 out of the 6 cases, we see significant improvements, and at least comparable even for the 6th course, using these meta informations in our model. And then looking at the attention layers, we try to identify what meta features are actually important. What does our model care about in terms of meta information? And we see that title, level, and long description get a lot of attention. The other meta features, I mean, they all help. We do an ablation study as well. But if you could choose any of these, they help a lot. And if you were to integrate these into your model when you're doing performance prediction, definitely these are the ones to start with. The second and the third and final question is, can fine-tuning a model based on previous iterations make the performance even better? So if you have access to these previous iterations, can we use them on top of a large model trained on 25 courses and transfer to the single course that is left out? And what we see is that it helps sometimes. This is our original result. So this is if we just train the model on previous iterations for 3 of these different courses. Then we take a look at just the meta model. So in making predictions on these courses that are held out just by using our model out of the box. And then we fine tune, which means we adjust the weights a little bit based on the previous iterations of this course. And what we see is that it helps when the information is similar. If the previous iterations are very close to the model that we're predicting on, then it makes sense. And otherwise, it actually hurts the predictions of this larger, more diverse model. So overall, what are the main takeaways? 1, training on a large model is helpful. And we release all of our models publicly. So if you're interested in using these to get out of the box predictions, please go ahead. We'd love to see it. 2, combining behavior and meta information actually helps a lot. 3, if you could choose any meta features, level, title, and duration are very helpful. And lastly, when these previous iterations are available and they are similar, you should use them to fine-tune this model so you can have even better predictions. There are some limitations of this work. Specifically, we are looking at MOOC courses offered in Switzerland. So looking at other universities and other world regions and a more diverse set of MOOCs would perform probably even better by having a larger model. We want to see if this model can also be transferred to different modalities. So flipped classrooms or blended courses, would it work? And lastly, can we use latent feature representations like autoencoders to extract features instead of simply creating these code bases to extract manual handcrafted features? And so lastly, if you take away anything from this presentation, large models combining interaction and metadata, super helpful. And using our models, educators can warm start predictions, and we encourage you to use them as well. Thank you very much.
Thank you so much. Is this on? Yeah. Is it? Okay. I'll come over here for questions.
Thank you. Great study. Very nice. I just have a quick question on the metadata. I was wondering why you didn't use some features that are pretty predictive of dropout rates, which would be dropout rates. And so past private, so DWs and ABC variables are pretty predictive of whether or not a student who is primed to drop out will drop out. And then the other variable, I was wondering, two variables in combination would be gender and URM, and then but in the metadata, the proportion of female and URM within the course is also predictive of dropout rates for when the ratio is low.
Definitely. I think it's a great question. Thank you very much. The reason that we chose not to use these demographic features was that sometimes instructors, especially for first-time courses, haven't already done this survey. They usually do it post hoc. And likewise, for dropout rates for a specific course, if it's a first-time course, they don't have access to that information. And so we want to make it as ubiquitous and easy to use as possible. I'm sure that that would probably improve the model predictions, but it wouldn't make it as generalizable. I think that's the takeaway.
Yeah, thank you, Vinitra. I have a question. Could you go into the curriculum or the context of your students? How likely does a digital signal processing student take the venture course in reality, or the French structure? Yeah. So how likely will they transfer in reality?
Probably not very likely. Just because they're in kind of different certificate programs and things like this, and very different instructors. And also the study was, all of the data is computed over 5 years, so the timing is different as well. The transfer is not for the students' transfer of knowledge. It's mainly, can we make predictions on courses? Transfer learning from the machine learning perspective of, can we train a model in one context and have it apply to a totally different context? So great question, but I don't think that the students have much overlap between many of these courses.
Okay, thank you.
Thanks for the presentation. I really enjoyed it. I actually have a bunch of questions, but I'll try to focus. One of the questions that I'd like to ask is, I see you aggregating data from lots of courses together and building one sort of generalizable model. What level of analysis have you done on that model in terms of, like, for whom is the bias of the predictions, like for whom is the model working best, and have you done any sort of examination of that question?
Really great question. No, we leave that in future work. I think it's very important, and I am working on some papers on bias on the side as well. But we just sheerly ran out of room, and my professor told me to stop doing experiments.
Push back, push back.
Really enjoyed your presentation. Was trying to deconstruct a TensorFlow model as I was looking at the slides. Maybe I should read a paper.
It's on GitHub.
Right. I wonder if you thought about the cohort effect. So students in different years vary. I don't know what are the reasons, but if you tune into that, since you're looking at the data over 5 years, maybe that factor could alleviate some of the transfer suppressing factors.
Could you explain the cohort effect in more detail?
Year over year, students are different. So if regression wise, you can introduce a intercept, right? So for this year, students are generally a tad smarter or a tad less capable. Again, I'm trying to formulate it in terms of neural network, and
I think I understand.
maybe
Yeah, it's quite a good point. So you're saying that as a course moves over time, some years have different student populations than others, and that can be a very good predictor across everybody. I see. I feel that with MOOCs, because the student populations are so varied, this is mitigated a little bit more than in, let's say, a traditional classroom with a cohort of students that changes year by year. And for a lot of these MOOCs, they are one-time offerings. So we don't have that longitudinal data. But at EDM, I'm working on another paper that has previous iterations. So I'll see you there.
we have time for one or two more questions, and maybe as we do these final questions, the next speaker can start to come up and get set up. But are there any questions either in person or online? Okay. So are they gonna ask themselves, or are you gonna read it, Renee? No question. Okay. Any more? Okay. Yeah.
Have you thought about, can your model predict, can you generalize your model to predict things other than just dropout? That would be one question. And the second question would be turning people's attention to a paper Renee wrote actually years ago, looking at unpacking what dropout actually means, that there are different things that we would all say are dropout, but that the student, what motivated the student to engage with the MOOC to begin with, it may not be dropout. So I don't know if you're interested in possibly looking at the classifications that they came up with in student motivation in your model to predict dropout for students who are actually dropping out, not students who are stopping because they got what they needed or something. So I guess there's two questions.
Super interesting. Thank you, Candice. So regarding the first question, I think that this model can be leveraged with just adding a couple of dense layers at the end to change the prediction task from pass fail to dropout to affect detection to whatever it is, because it's supposed to capture a generalized sense of student knowledge and their interactions. So maybe future work. But I think it is really the way to go. And the second, I would be very interested. I haven't read this paper yet, but I will definitely check it out. And I think it would be quite cool to include this clustering of student motivation somehow into the model, or maybe create that as an additional predictor and have that influence the predictions as well.